Hello everyone, welcome to our discussion of section 7.5 where we will be talking about more techniques of solving trigonometric equations. Now before that, I'm going to briefly cover a subject that I was asked about by several people, and it's about finding the inverse of trigonometric functions for which there is no button on the calculator. Now, several of the trigonometric functions are reciprocals of each other. So we can make use of that relationship in order to find the value of trigonometric functions for which you don't have a button on your calculator. For example, a cosecant function is the reciprocal of the sine function and vice versa. The secant function is the reciprocal of the cosine function and vice versa, and the cotangent function is the reciprocal of the tangent function and vice versa. So we can make use of that to not really care if we don't have a button on the calculator. We can make use of these other buttons, but we will go over a few examples talking about that. Then we will talk about using trigonometric identities and formulas that we've covered so far to convert an equation containing multiple trig functions to an equation containing a single trig function. Now remember, when in basic algebra, when we were solving for x was just one variable, right? So this is no different than that. If we have cosine and secant in the same equation, we want to convert both to one of those trigonometric functions. That way we'll be able to solve the function. Next, we will talk about specific solutions of trigonometric equations. These are usually we call them, let me add a bit to this. When we say specific solutions of a trigonometric equation, we're talking about within some interval. So within the interval 0, 2 pi parenthesis. Okay, so the open parenthesis means that we approach to 2 pi, but it'll never be 2 pi because 0 already covers that. So if I put a closed interval here, then it'll be the same thing as 0. We don't want that. We just want to so this will be an open interval on this side. So we will evaluate the solutions of trigonometric equations within this interval. Okay, but that covers everything from 0 to 2 pi. Finally, once we talk about specific solutions, then we should also talk about all solutions of a trigonometric equation. In fact, maybe I should have numbered this 3 and that one 4. The reason is because before we find the specific solutions, normally we find all solutions anyway. And then we can find the specific solutions. We'll do several examples. You'll see exactly how this works. But this is okay, but maybe it was even better if I had numbered this 3 and that one 4. Okay, so first then, as I promised, let's talk about how we can find the inverse of trigonometric functions for which there is no button on a calculator. So suppose we want to calculate the inverse cotangent of 5.49. Okay? Of course, if you look at your calculator, you're not going to find a button for inverse cotangent. You will find a button for inverse tangent, though. And cotangent and tangent are inverse or are reciprocals of each other. So maybe for that reason, the manufacturers didn't see a point of cluttering the calculator buttons with an additional button that we don't really need. We can make use of the inverse tangent function on our calculator. So let's mention that the cotangent function, and we'll get to the inverse cotangent function, but the cotangent function and the tangent function are reciprocals of each other. So if you want to calculate the inverse cotangent of that, you can take the reciprocal of this value and find the inverse tangent of the reciprocal of this value. So this is what I mean. So thus, the inverse cotangent of 5.49 is equal to inverse tangent. Now we're using tangent, inverse tangent, right? And tangent and cotangent are reciprocals of each other. So I need to take the reciprocal of that, 1 over 5.49. So now if you set the, and by the way, you should at this point set your calculators to the radian mode, because as you know, you can your calculator can be set either in degrees or radians. So you want to set it to radians at this point. Okay, so now we can use, there's certainly a button on our calculator with the inverse tangent button on it. And I didn't bring, or I forgot to bring my calculator with me, but this is, that's really, once you know how these two are connected, using the button is really not that difficult. So you can activate the inverse tangent button on your calculator. It's usually activated with a blue button or something like that. And then in parentheses, you can put 1 over 5.49. And we do that because the tangent and cotangent are reciprocals of each other. Okay, and so by the way, set your calculators to radian mode as opposed to degree mode. Okay. All right. So if you do that and double check with this, you should get 0.1802 radians. Okay, so this is the answer you should get. Again, this solves the issue of not having an inverse cotangent button on our calculator. Let's do another one for the inverse secant function. And of course, secant and cosine functions are reciprocals of each other. So we can make, or we can take advantage of that. And we can bypass not having a button for the secant or inverse secant function on our calculator. So here we want to calculate the inverse secant of 4.328, like that. So I would strongly encourage you to pause the video and answer that. And as a matter of fact, let me put another example so you have that. And let's put another example here so you can pause the video, answer these on your own, and then come back to the video and see what answer I got. And this is inverse cosecant of 1.37. Excuse me. 1.37. Okay. So for these two examples, just pause the video and run your own calculation and then come back to the video to see if our answers agree. Okay, I hope you've done that. and you're back. So the secant, we know that the secant and cosine functions are reciprocal of each other. Thus, so that means that the inverse secant of 4.328 can be written or calculated as the inverse cosine of 1 over, take the reciprocal of that, 1.328. Okay? And once again, when you calculate, I hope our answers agree. This is 1 point, this is what I got. And of course, this measure is in radians. So I keep mentioning that because if you have your calculator set in degrees mode, and if you run this calculation, you're going to get a different answer. So please make sure that your calculator is set to the radians mode. Okay? All right, so let's do this one. So once again, we know that the cosecant function and the sine function are reciprocals of each other. Okay. Thus, to calculate this value then, we can write inverse sine of 1 over that quantity. And certainly we have a button on our calculator for the inverse sine function. And so when it's sent to radians, we should all agree that the answer is 0.8182 radians. Okay. Okay, so I hope these few examples help those of you who might have had similar questions about these buttons that are missing from our calculators. Okay. Okay, so in this next example, throughout this section, we will just solve examples because we've already learned about techniques here. There's no new techniques discussed in this section. It's just applying them to solving trigonometric equations. So we'll do example after example after example. So here we want to solve for the value of theta. We'll do a number of these examples. So here is, let's label this as part A. We have cosecant squared theta equals cotangent of theta plus 3. You don't really need these parentheses. I just have a habit of using them to give a visual clarity, a sense of visual clarity to what's what. This is the argument of this function. Okay. Okay. So one of the formulas we learned for solving this. So this is the solution. So we already know that cosecant squared theta is equal to 1 plus cotangent squared theta. This is one of the formulas that we learned before. Okay, so we know that right, and we want to rewrite the equations like this where you have two trigonometric functions. we do want to convert one to the other, so we end up with an equation with one type of trigonometric function, so we can solve it. It's just like that x that I mentioned earlier, x squared plus 2x minus 3. And then we would solve, in basic algebra, we would solve the equation for x. So here we have two different trigonometric functions. We want to convert either this to that or this to that. That way we'll end up with one single trigonometric function in the whole equation. Okay, that's the objective of applying this formula. So we know that the cosecant squared theta, which is the left side of our equation here, is equal to 1 plus cotangent squared theta. So let's replace it with this equivalent. Okay. Therefore, we have on the left side, instead of that, we have 1 plus cotangent squared theta equals what we had on the right side. Now we have this equation in terms of cotangent, right? So let's move everything to one side and set the equation equal to 0. So we have 1 plus cotangent squared theta. I'm going to move this to the left, so it'll be the sign, algebraic sign will change to the opposite. I will move the 3 to the left, and it will change the algebraic sign to the opposite, equals to that. So let's put these things in order. We have cotangent squared theta minus cotangent of theta minus 3 plus 1. We have minus 2 equals 0, right? So now we have what we're really very familiar with, actually. This is a quadratic formula in terms of cotangent function, right? Okay, so let's use, back in Pre-Calculus 1, or Math 126, we discussed the method of U substitution, which was very useful. This is one of the techniques we learned about. Well, let me do a refresher in case you've forgotten what the technique was, but let's do this. So this is how the method works. Let U equals cotangent of theta. Now we're going to, in this equation, we're going to replace it with U. So if U equals cotangent theta, then U cotangent squared theta would be U squared. This would be minus U, and that would be minus 2. And then this is a very easy quadratic equation that we can quickly factor by saying U minus 2 times U plus 1 equals to 0. And of course, U is cotangent theta, so we can replace it back. Cotangent theta minus 2 times cotangent theta plus 1 equals 0. Okay? Very easily we were able to factor this out. But remember, the first step was to convert this equation such that there is a single type of trigonometric function in it as opposed to two different ones. Okay, that was the first step. All right, so now if we're back on track again, right? So because we have this equation fully factored. So if cotangent of theta minus 2 equals 0, then we know that cotangent of theta must be equal to 2. Now, on our calculator, as we were mentioning, there is no cotangent button, right? There is no cotangent button, or there is no inverse cotangent button. So we can then use the inverse tangent or inverse tangent buttons. So, but let's use the inverse cotangent because we're looking for an angle, right? We're looking for an angle. The theta is what we're looking for. So to find an angle, we definitely need to use the inverse trigonometric function. So let's convert this to the inverse trigonometric function. So cotangent, inverse cotangent of 2 must be equal to theta. Right? So then therefore, since like we were saying on the previous page or examples, since there is no button for inverse cotangent, let's convert this to the inverse tangent. But remember, the tangent and cotangent are reciprocals of each other. So when we make the transition from inverse cotangent to inverse tangent, then we ought to take the reciprocal of that 2, which would be 1/2. So now you can use your calculator. Please do that on your own. So use the inverse tangent of 1/2. Find that with your calculator, of course, set to radian mode, and see if you get the same answer that I got, which is theta equals roughly, and let me put the approximate symbol here. Theta is approximately equals to 0.46 radians. Okay, not degrees, radians. So we know that the cotangent and tangent functions have period pi. Okay, so before I do that, we can actually wrap this up before I go to this factor, because we're going to need this solution is from this factor. We also have to obtain the solution from this other factor. So let me move this up. We know that cotangent of theta and tangent of theta have period pi. Okay. Thus, all the solutions are that plus k pi, where k is just any integer, 0, 1, -1, whatever. So this is all the solutions of theta. So theta is equal to 0.46, which is approximate value we found, plus k pi. And k is any integer. So k, any integer, including, so of course when we say integer, it includes 0 as well. Okay, so, and before I box this, I want to find the other solution as well. So let's go back up to this one. Now, if cotangent of theta plus 1 equals 0, then we have cotangent of theta equals -1. Of course, this is, again, we don't have the button for this. So to find the theta, let's take the inverse of the cotangent function. We have inverse cotangent of -1 equals theta. Of course, we don't have that button, as we discussed. So let's convert this, but take the reciprocal of -1. What do you get? You get -1. So inverse tangent of -1 equals theta. And of course, we know that for the tangent of pi over 4, in this case minus pi over 4, is, because it's negative, so it must be in the fourth quadrant, is theta. So theta is equal to minus pi over 4. Okay? All right. So for this one, we don't really need to even use the calculator, because we know that from the special trigonometric values table that we discussed earlier. We have that from that. So once again, tangent and cotangent, as we mentioned here, have period pi. So all solutions then would be from this one. It would be theta equals minus pi over 4 plus k pi. Okay, pi because the cotangent and tangent have period pi, and k goes through, because these are periodic functions, so it goes through all the solutions. So now we can box this. So let me box this like that. Okay. These two together, with k being any integer, form all the solutions of theta in that equation that we had above, that one. Okay, we found all the possible solutions. If they ask us to find a specific solutions, they usually say find a specific solutions between 0 and 2 pi. Then we'll do something else, and we have examples like that too. And your book is just excellent book, and it's got excellent, very clearly explained examples, and I hope that you take the time to read the textbook as well as going through these examples with me. Okay, so here's another example. We have cosine squared theta minus 2 sine theta cosine theta plus sine squared theta equals 1. Now, clearly, you have more than one trigonometric function here. You have the sine and cosine. You have two types of trigonometric function. So if we want to solve for theta, we better change this equation so we have either sine or cosine. Then we'll solve it. Okay? So the first thing we notice, and let me begin the solution from here. The first thing we notice is that, notice that the cosine squared theta and sine squared theta, we have a formula for that, right? Cosine squared theta plus sine squared theta, what is that equal to? Do you remember? We know that cosine squared theta plus sine squared theta is equal to 1. Isn't that neat? It's pretty neat. It simplifies this equation greatly, so we can add these and replace these two and just with 1. So let's do that. If we do that, we get 1 minus 2 sine theta cosine theta, which is that, equals 1. Of course, if we're solving for theta, then let's isolate terms that have theta in them, just like any other equation we solved back in basic algebra classes. So let me move this one to the other side. We have minus 2 sine theta cosine theta equals 1 minus the other one. So we have minus 2 sine theta cosine theta equals 0. Of course, we can divide both sides by minus 1. So not by 2. We have a very good reason for keeping 2, but dividing both sides by negative 1, what do we get? We get 2 sine theta cosine theta equals 0. Okay, divide both sides by negative 1. Now, I kept the 2 because of this. Recall, we have a double angle formula, right? Recall that recall D, not that, recall D double angle formula sine of 2 theta equals 2 sine theta cosine theta, right? So in that, let me put parentheses like that. So that, the left side is that, right? So we can replace this with sine 2 theta. So let's do that. So sine 2 theta equals 0, right? That's coming, this is coming from that. and using this identity that we knew about. So then so several scenarios happen here. If this equation is to be 0, then 2 theta could be equal to 0, right? What are the different sign values that are equal to 0? We have, if 2 theta is equal to 0, then theta can be equal to 0. That's one of the theta values that will make this equation true. What other values are there? So let's say if 2 theta equals pi, right? Sine of pi is equal to 0. So 2 theta equals pi, then theta would be equal to pi over 2. Then if 2 theta, well, we might as well do that. If 2 theta is equal to 2 pi, right, then theta is equal to pi. So all these theta values will make this equation true. So therefore there are the 3 specific solutions we have. But sine has, we already know sine has a period 2 pi, right? So recall that, this is very important, recall that sine function, or sine of x, has period 2 pi. So if we want to find, these are specific solutions. If we want to find all solutions, we can simply add each solution to 2 pi and put a k, because k means k is any integer, and it takes that solution through infinitely many cycles, because these are trigonometric functions and they're periodic. So with that, this is what I mean. So thus, these are all solutions. So all solutions are, let's just add 2k pi to each one of these. So theta with 0 plus 2k pi is simply 2k pi. 0 equals pi over 2 plus 2k pi. So pi over 2 plus 2k pi. And then finally pi plus 2k pi. Okay? And k is any integer. Let's box this and say that k is any integer. So we do this in order to show all solutions. That's what we're showing in the box here. Those are specific solutions within 0 to 2 pi. These are all solutions. Okay? All right. So here we have another equation. We have tangent of theta minus 3 times cotangent of theta equals 0. And we're, of course, looking for theta. Once again, notice that we have 2 different trigonometric functions. We want to convert these to one form. Either convert this to cotangent or convert this to tangent. Okay? So let's convert the cotangent to tangent, because we know if we end up with a value that we have to use our calculator with, then we can use that. So let's convert cotangent to tangent. So recall, and this is the solution. So solution here. Recall that cotangent of theta is equal to 1 over tangent theta, right? The two are reciprocals of each other. So we can replace that one with minus 3 times 1 over that. So let's do that. So thus, we have tangent theta minus 3 times 1 over tangent theta, okay, equals 0. And then we have tangent theta minus 3, multiply that over tangent theta equals 0. And so we can take the common denominator here. Let's see, tangent squared theta minus 3. Yes, so let's take the common denominator. Common denominator would be tangent theta. The denominator here is 1. We can multiply it by tangent theta over tangent theta to get the common denominator. So we end up with tangent squared theta minus 3 equals 0. Okay? All right, so now we can multiply both sides by tangent theta to get rid of this fraction. So multiply both sides. These are all techniques we learned in basic algebra, right? Taking the common denominator, multiplying both sides by tangent theta to get rid of the fraction. Now you're seeing the benefits of learning those techniques. So we get tangent squared theta minus 3 equals 0. Well, from this, we know that then tangent of theta, if we take the, or tangent squared theta equals 3, and take the square root of both sides, what do we get? We get tangent of theta equals, plus or minus, of course, by square root property, plus or minus square root of 3. Okay? From the table of special trigonometric values, we know that the, let me bring a scratch paper here. Let me move this up a little. Well, so if this is the unit circle, then the tangent is going to be equal to square root of 3, positive square root of 3 in the first quadrant. And also, so if this is tangent of theta is equal to square root of 3, then theta, we remember from the special trigonometric value tables, the table that we've been discussing throughout the semester, the theta is equal to pi over 3. And we also have a negative square root of 3. And tangent is negative in this here. If tangent of theta is equal to minus square root of 3, then theta would be, that is pi minus pi over 3. So pi minus pi over 3, or theta is equal to, take the common denominator, we have 2 pi 3. So this one is 2 pi 3, and that one is pi over 3. What about the other ones? Because we have an angle here, which would be pi plus pi over 3, or it would be 4 pi over 3. So this one would be 4 pi over 3, right? Which will give us square root of 3, because cosine is negative, sine is negative, sine divided by cosine, it's negative divided by negative is still positive. And we have this one also. This would be, so this is 2 pi minus pi over 3. Right? So this would be 5 pi over 3. 5 pi over 3, this one, which is the result of 2 pi minus pi over 3. So what about these? Well, notice that the tangent function has period pi. So if you have the pi over 3, this one, and then say plus pi, you get this one, the one that I'm showing with red. If you have 2 pi over 3 and you say plus pi, you get this one. So if you take, to find all the solution, all we needed was pi over 3 and 2 pi over 3. To find all the other ones, including the 4 pi over 3 and 5 pi over 3, for which the result would be plus or minus square root of 3, we can just say plus pi, because the period of tangent function is pi. And if we want to extend this to all possible solutions of theta, we can add a k pi, k being any integer, 0, 1, 2, 3. So you're creating this harmonic function solution where the solutions go through infinitely many cycles. Okay, so we can do that. So because of that, then therefore, well, let me, because I drew it there, I drew that picture there. Let me also draw it here, a little one. So you have it in your notes. And so we have the unit circle. And we know that that tangent of this, so this theta is equal to pi over 3. Tangent of pi over 3 is plus square root of 3, positive square root of 3. Then, by the same token, we have here on this side, we have 2 pi over 3, which is pi. If you say pi minus pi over 3, pi minus this piece, pi over 3, you get 2 pi over 3, which is this angle, this large angle from the positive x-axis all the way to this one. This line being the terminal side of the 2 pi over 3. Okay? So, I mean, I drew this arrow maybe in the wrong location, but this, I should have drawn, I will correct this. So 2 pi over 3 is this angle. But that's just a reference angle for this. So let me correct, I will erase this arrow in favor of that one. That angle is 2 pi over 3, which is that. Also has tangent, which is equal to minus square root of 3. And because tangent has period pi, we can construct all the solutions of theta. So these ones and that one. So I don't want to make this drawing too cluttered, but that angle is 4 pi over 3, that one. And this one is 5 pi over 3, going all the way around to this point. Okay? So that all the way to that, that's 5 pi over 3, which has a tangent 5 pi over 3 is equal to minus square root of 3. And of course, that one, this angle would be 4 pi over 3, which would have a tangent of plus or positive square root of 3. So, but these are the two important angles, the pi over 3 and the 2 pi over 3, because based on these two, we can generate all the other ones. So, therefore, So specific solutions are, so we have theta. Let me put an arrow from here. So theta is equal to pi over 3 comma 2 pi over 3. Thus, all the solutions are and let me just remind everybody that tangent has period pi. As this is important as we write all solutions, that all the solutions that I'm talking about, it's important to remember that tangent has period pi. So we have theta equals this one, pi over 3, plus k pi. Pi because that's the period, k because we're taking this solution through infinitely many cycles. K can be anything, any integer. And the second set of solutions will be 2 pi over 3 plus, of course, k pi again. Okay, so these are all the solutions, and k is any integer. Okay, so when you go through 0, 1, k0, k1, and so on and so forth, you're generating these other solutions, including 4 pi over 3. Let me put that also, since I put, so this is 4 theta equals 4 pi over 3. Okay. This drawing, I know, it's a little bit crowded, but follow what I've done through the these symbols and arrows here. Okay. And if you have any questions, please let me know. These are, if you're clear, the reason I'm asking, make sure you clear your questions, is because if you can follow this one example from start to finish with no questions, that is, if you have questions, you should bring them to me. Then if you understand this one example fully, you understand a whole host of examples. Okay, that's why I encourage you to make sure that you get answers to your questions. All right, so let's do another example. So here, the example is saying that given this trigonometric function, 2 sine of 3 theta plus 1 equals 0, given that, we want to find A, all the solutions. That's where all the solutions, as soon as I say this, you should remember that we use the k, right? K gives us all the solutions. Find all the solutions. B, find all the solutions within the interval 0, 2 pi. And this side is the parentheses. Okay? All right. As I said earlier, your book is an excellent book, and it does a very good job of explaining examples like this. So in addition to what I'm doing here, I hope you're going back to your textbooks and also reading those as well. Together, I'm sure you'll develop, with these examples and your textbook, I'm sure you'll develop a very good understanding of this topic, because you don't need to memorize much. Yes, we have formulas that we need to remember, But once you know how the techniques work, then you'll have a much easier time of solving, answering questions like this. All right, so this is an easy equation to solve for theta, first of all, right? So let's do that. So we're answering part A first. So let me put A here. Okay, so let's solve for theta using that. We have 2 sine 3 theta plus 1 equals 0. Therefore, we have sine 3 theta equals minus 1/2, right? So whatever this angle is that we're solving for theta, we're looking for that, whatever that angle, it should give us a sine value that is negative. But in which quadrant are sine values negative? We can quickly remember that by drawing I'm going to draw a very small figure here, a small diagram. Okay, and the sine is negative in the 3rd quadrant and the 4th quadrant, right? That's because sine has to do with the y-axis. So either here, if we're here in the 3rd quadrant, we must be either here or here in the 4th quadrant, then the sine is going to be negative. Then the next question is, the sine of what angle is 1/2? Well, from the special, this is an easy number, from the special trigonometric values table that we've been using, that would be pi/6, right? Or 30 degrees. So then the one angle, so we're looking for these 2 angles. This one, so one angle we're looking for is that one. What is that angle? Because we need that because that will give us minus 1/2. The other one is that one. That one. Okay? So we're looking for those 2 angles. All right. So it's easy to find both, because that one is simply pi plus pi/6. Pi would be 0 to pi, and then plus pi/6, which is that piece. Okay, so let's write it down. So pi plus pi/6, it's going to give us 7 pi/6. That's that angle. This one in here. So let me write it. So that's 7 pi/6. What about this angle? What is the measure of that angle? That's easy too, because that's pi/6 short of being 2 pi. So we can say 2 pi minus pi/6 will give us this angle. So 2 pi minus pi/6 is equal to 11 pi/6. Okay? So that's the bigger angle right there, the one that is going this way. This one is 7 pi/6. The bigger angle is 11 pi/6. Okay, so now we figured out what 3 theta is going to be equal to. Okay? 3 theta is going to have to be equal to 7 pi/6, or 3 theta is going to be equal to 11 pi/6. But remember, sine has what period? Do you remember that? Sine has period 2 pi. So if we take this through 2k pi, we're going to find all the solutions. Because we're going to need to remember the period of all these trigonometric functions if we're asked for the all solutions piece. So Let's remember that because we're answering part A, all the solutions, right? So recall that sine function has period 2 pi. 2 pi, okay? Why do we say that? Here is why. We have 3 theta that has to be either equal to 7 pi over 6. So 3 theta equals 7 pi over 6. That way we can get sine of that, we can get minus 1/2, right? 7 pi over 6. Oh, but wait a minute. We're looking for all the solutions, not just that one solution. So what do we have to do? Well, the period is 2 pi, so plus 2k pi. And k is going to give us all the solutions. And 2 pi being the period. So what about the other one, 11 pi over 6? Why did we need that? Well, that's going to give us the other set of solutions. So we have 3 theta can be equal to 11 pi over 6 as well. 11 pi over 6, but we're looking for all solutions, so plus 2k pi, because sine has 2 pi period, and k is going to give us all solutions. 2 pi is the period, we're going to need that. K gives us all the solutions. So have we answered the question yet? No. Why not? Well, because we found 3 theta. 3 theta is equal to that, 7 pi over 6 plus 2k pi. So how do we find theta? Theta, we multiply both sides by 1/3, right? So multiplying both sides by 1/3, we solve for all theta, which is what they're asking here, all the solutions. Okay, so let's do that. We have theta equals, I'm multiplying both sides by 1/3 in here and in here. So we have 7 pi over 18 plus 2/3 k pi. And then here we have theta equals 11 pi over 18 plus 2/3 over k pi, or 2/3 k pi. So now that's all the solutions. And k is any integer. Okay? So we answered part A, which wanted us to find all solutions right there. That's all the solutions. Okay, the part B says all the solutions within the interval, with this interval, 0, 2 pi. So how do we do that? Well, we can use this very easily to give us the solutions within 0 to 2 pi. So we start with k equals 0. Then we go to 1, k equals 0, k equals 1, k equals 2. When do we stop? When do k calculations or k settings stop for solutions within 0 to 2 pi? Whenever you put a k value here, that when you multiply it by 2/3, it's going to give you equal to 2 pi, you stop. In which case that is. I mean, before that you should stop. In this case, it would be, what k value would give you 2 pi here? Can you see it? Since k is any integer, right? It could be negative, positive, but we go with the positive one. It makes no difference. It's just going through all the cycles, back and forth. But if we start from 0, That's fine. What about 1? That would be fine too. It's still less than 2 pi, right? 1 times 2, 2 pi over 3, that's less than 2 pi. How about 3? How about 2? 2, 4 pi over 3. Is this 4 pi over 3? Is that less than 2 pi or larger than 2 pi? 4 pi over 3 is less than 2 pi, right? So it's still allowed. K can be equal to 2. It can be equal to 0. It can be equal to 1. It can be equal to 2. What about 3? Can K be equal to 3? Well, 3 times 2 is 6. 6 divided by 3 is 2 pi. 2 pi, we can't have that. Right? 2 pi parentheses. We cannot get to 2 pi. So K cannot be 3. So K can only be 0, 1, and 2. Okay? So part B, for solutions within the interval 0 to 2 pi, simply set K equal to 0, 1, and 2 in each one. So how many, let me ask you this, how many specific solutions then we're going to have within this interval? If K is going to be 0, 1, and 2 in both of these, how many solutions are we going to have within this interval? 6, right? Because in this equation, we're going to set K equals 0, 1, 2. That's going to give us 3 solutions. Then we're going to come here and set K equals 0, 1, 2, and we're going to get 3 solutions from here. Collectively, we're going to have 6 solutions within 0 and 2 pi. Like I said, you cannot use 3 or anything larger. Why? Because you're going to go outside of this interval. If you use 3, you're going to get 2 pi. You can't have 2 pi from here. Okay? You can't. So that's why. All right, so let's calculate, make these calculations. So for theta equals, or when, I should have said when 7 pi over 18 plus 2/3 K pi, and then when theta is equal to 11 pi over 18 plus 2/3 K pi. Okay, so for K equals 0, all right, I'm trying to keep everything on the screen. K equals 0, then theta is simply going to be 7 pi over 18, right? Because that whole thing is 0. On this side, if K equals 0, then theta is going to be, that term is going to drop out. We're going to have 11 pi over 18. So if K equals 1, then we're going to have, from this equation, we're going to have theta equals 7 pi over 18 plus K equals 1, we get 2 pi over 3, right? 2 pi over 3. Then, so that's one answer, that one answer. That's 2 of the answers so far. And then we're going to have theta equals, take the common denominator here, 18. We get 7 pi plus 12 pi. So we're going to get 12 pi plus 7 pi, 19 pi over 18. That's another solution here. 1, 2, 3. Let's set K equals 1 in this equation. So we have 11 pi over 18 plus 2 pi over 3. When k equals 1, we get 2 pi over 3. Take the common denominator, which is 18. All right? We get 11 pi plus 6 times 2, 12 pi, which is equal to 11 pi plus 12 pi. That's 23 pi over 18. Right? That's another solution here. Here. We have one more to go, right? Or two more to go. K equals 2. K equals 2. We need to evaluate both equations at k equals 2. Okay, let's do that. So k equals 2, then we have theta equals 7 pi over 18 plus 2 times 2, 4 pi over 3. Then take the common denominator, and we have 7 pi plus 24 pi, and that's going to give us 7. That's 31 pi over 18, and I'm getting too close to the bottom of the screen there. Like that. And then let's set k equals 2 on this side. We get theta equals, there, 11 pi over 18 plus 2 times 2, which would be k, 4 pi over 3. Take the common denominator. We have 11 pi plus 24 pi. That's going to give us 11 pi plus 24 pi. We get 35 pi divided by 18. So we have this one and also this one. So you can see all, let me bring this down a little bit, all 6 solutions. 1, 2, 3, 4, 5, 6. So let's write them down, all the specific solution. All of these are solutions within 0 to 2 pi. So the solutions within 0 to 2 pi are as follows. Theta equals, I'm going to start with that one, 7 pi over 18. Then I'm going to go to that one, 11 pi over 18. Come here, 19 pi over 18, and then go over there, 23 pi over 18. Come back here, 31 pi over 18, and then finally 35 pi over 18. Okay, let me move this up so you can see it better. Like that. Like that. So that's all the specific solutions within 0 to 2 pi. So you see how, in order to find this, we'll first have to find the all solutions with the k involved. Okay. So let's move to another example. Here, and let's call this, I believe that one was A, or the previous example. Well, let's call this another example. So, example, given secant of 4 theta minus 2 equals 0, part A, we want to find all solutions of theta, and B, all solutions of theta within this interval, 0 to 2 pi parenthesis. Okay, so let's start with A. We want to find all solutions of this theta, part A. Okay, so we already know that, let's solve this for secant first. So secant of 4 theta minus 2 equals to 0. Therefore, secant of 4 theta equals to 2. So we know that then, therefore, inverse secant of 2 must be equal to 4 theta. Okay? But we know that on our calculator, we don't really have a button for inverse secant, but we do have a button for inverse cosine, right? And cosine and secant are reciprocals of each other. So we can say, we can convert this to cosine by saying inverse of, when we switch to cosine, we need to take the reciprocal of that. Inverse cosine of 1/2 equals 4 theta. Okay, so cosine of what angle is 1/2? That's pretty easy, right? We can remember it from the special trigonometric values table. Cosine of what angle is 1/2? That's pi over 3. And of course, that's just one of the two, because there is also 5 pi over 3 that has cosine equal to 1/2, right? So let me draw a little diagram here. So this one, this is pi over 3, for which the cosine of pi over 3 would be equal to 1/2. But on this side, which is 2 pi minus pi over 3, and that's this angle. Let me show it with red. That angle is 5 pi over 3. Okay, so for both of these angles, cosine is equal to 1/2. That we need to know that, because then when we find all solutions of theta, then we have to start from here and go 2 pi, and then start from 5 pi over 3 and go 2 pi to find all solutions. Okay, so based on that, then we know that therefore theta is equal to pi over 3 comma 5 pi over 3. 4 theta. Sorry about that. So this is 4 theta. So we found 4 theta equals, these should be equal to one of these, either this one or that, in order for us to have a cosine equal 1/2, or the secant that would equal to 2. Secant of 4 theta equals to 2. Okay? So let's remember that cosine function has period 2 pi. Recall that cosine of x has period 2 pi, right? Tangent and cotangent have period pi. Cosine and sine have period 2 pi. Okay, so now we need that in order to find all solutions. So we have 4 theta equals pi over 3 plus 2k pi, right? 2 pi, right there. And k takes us through all the possible solutions. Then, for the other one, for 5 pi over 3, we have 4 theta again equals 5 pi over 3 plus 2k pi. Okay? Have we answered the theta question? No. We found what the right side is equal to 4 theta, but how do we find theta then? Any ideas? How do we find theta? Well, we divide both sides by 1/4 or by 4, or multiply both sides by 1 over 4. So let's do that. So multiplying both sides by 1 over 4, we have theta equals pi over 12 plus 1/2 k pi. And here we have theta equals 5 pi over 12 plus 1/2 k pi. Okay, so this is all the solutions, and k is any integer. So what about, so we answered this question, all solutions of theta. What about all solutions within 0 to 2 pi? Well, first we have to establish how many k values we can go through. So if k is equal to 0, we're okay, right? K is going to be, let me use my scratch paper here. If k equals to 0 here, we're okay, right? We're finding all solutions in this interval, 0 to 2 pi. So notice that on this side we have a parenthesis, so we can never be 2 pi. We can be 0 because we have a bracket here. We can be 0, but we can never be 2 pi. Okay? Because that would be outside of this interval. So if k is equal to 0, we're going to be in this interval. So this is okay. What about if k equals 1? Can we use that? Sure, we can use that because we have, if you substitute for k with 1, you get pi over 2. Pi over 2 is within this interval. So this is good too. How about if k is equal to 2? Can we use that? Well, if you substitute for k with 2 here or there, you get pi. 2 over 2 is 1. 1 times pi is pi. Pi is within this interval, so yes. How about if k equals 3? Can we use that? Well, let's see. If k is equal to 3, we get 3 pi over 2. 3 pi over 2 is well within this interval, so yes, this will work too. How about 4? If you have 4 here for k, 4 over 2 is 2, 2 pi. 2 pi is equal to 2 pi, so we can't have that. We cannot have 2 pi. There's a parenthesis here. So that would be, if you put k equals 4, you get an answer that is outside of this interval, right? Because you're going to get 2 pi plus something more. We can't have that. So k cannot be equal to 4 or larger. So k can be equal to 0, 1, 2, and 3. Having said that, how many total solutions are we going to have within this interval, 0 to 2 pi? How many total? If you said 8, you are correct, because 1, 2, 3, 4 from this equation, 1, 2, 3, 4 solutions from this equation, total 8. So k can be 0, 1, 2, and 3 only. Okay, I'll try to fit all of this in the remainder of this page. So this is finding all the solutions within 0 to 2 pi. Okay, so we have theta for let me, for the sake of saving paper space, let me do it this way. So I will use my thicker marker here. So from here, and then on this side, like that. That way I don't have to rewrite those. But so we have, if k equals 0 from this one, we get theta equals pi over 12, right? From that one. What about here? If k equals 0, we get theta equals 5 pi over 12. So that's two of the solutions. This one and this one. If k equals 1, then theta would be pi over 12 plus pi over 2. And then that one is equal to, let's see, so we have 7 pi over 12. All right, there you go. On this side, if k equals 1, we have, I'll try to keep this on the screen. Let me move this up like that. And then we have theta equals 5 pi over 12 plus pi over 2. And that'll be equal to, after taking the common denominator, we get 11 pi over 12. Like that. So if k equals 2, then theta is equal to pi over 12 plus 2, k being 2 would be 2 over 2 is 1 pi. So it would be plus pi. Take the common denominator here. We get 13 pi over 12. So that's another solution within 0 to 2 pi. Within all these solutions are within 0 to 2 pi. If k is equal to 2 here, then we have 5 pi over 12 plus pi again. So we have, this time we have 17 pi over 12 all right, like that. So we have, if k is equal to 3, we have theta is equal to pi over 12, we're plugging in here, plus half,
3k, when k is equal to 3, we have 3 pi over 2. So that will be 3 pi over 2. Take the common denominator, which is 12. So we get pi plus 18 pi. We get 19 pi over 12. So that's another solution. And then if k equals 3 on this side, we have theta equals, let's plug in here, 5 pi over 12 plus 3 pi over 2, and the common denominator 5 pi plus 18 pi, so we get 23 pi over 12, like that.
Okay, so we found all 8 solutions. So the specific solutions within 0 to 2 pi are solutions of theta. Let me move this up a little bit. Solutions of theta within 0 to 2 pi are theta is equal to pi over 12, 5 pi over 12, 7 pi over 12, 11 pi over 12, 13 pi over 12, 17 pi over 12, 19 pi over 12, and 23 pi over 12. Like that. Okay. So I hope things are starting to make sense about these things. So here we want to have, so given this equation, tangent of theta over 4 plus square root of 3 equals 0, we want to find A, all solutions of theta, and B, all solutions of theta within 0 to 2 pi, parenthesis. Okay? So here we have the first one, A. So we can easily solve this for tangent of theta over 4, right? So let's do that. So given this, we have tangent of theta over 4 equaling minus square root of 3. Now, this is an easy number because it is, square root of 3 is in the table of special trigonometric values. And we know that for, first of all, for the reference angle, so if we disregard the minus, theta over 4 would have to be pi over 3. So tangent of pi over 3 will give us positive square root of 3. But we have a negative there. So where is tangent of angles is negative? Let's draw a quick diagram to help us remember. So this being the first quadrant, second, third, and fourth quadrant, if you're here, all trigonometric functions in the first quadrant are positive. So this angle is not here. If you're here,
here the sine or the y-axis would be positive, the cosine or the x-axis in this quadrant is negative. So tangent is sine divided by cosine, which would mean positive divided by negative. So tangent would in fact be negative in this quadrant. So here, so if the angle is 2 pi over 3, which is pi minus pi over 3, that would be 2 pi over 3, we're going to have a minus square root of 3 result. Tangent of 2 pi over 3 would be minus square root of 3. Where else is tangent negative? Would it be negative here? No, because here the cosine or the x-axis is negative and the sine or the y-axis is positive. Negative. So negative divided by negative is positive. So tangent would be positive in the third quadrant. How about here? Yes, tangent of angles in this quadrant, fourth quadrant, would be negative because the cosine or the x-axis is positive and the sine or the y-axis is negative. Negative divided by positive is negative. So another angle for which we would have tangent negative would be 2 pi minus pi over 3, which is 5 pi over 3. So for this angle, which is 5 pi over 3, the tangent would be, again, negative square root of 3. So let me ask you this. What is the period of tangent function? It is pi, right? We need to remember that when we answer all solutions of theta. So from this we can say that theta over 4 it would be equal to, just from our memory of the special trigonometric values table, right? You could use your calculator for this, but this is easier. If you remember those few angles for which we gave that table, it's easier that way. It's quicker. So theta 4 would have to be either equal to 2 pi over 3 or 5 pi over 3. Now recall that tangent function has period pi. Okay? So that means theta over 4, so we're finding all solutions now, right? So theta over 4, let me start here. So theta over 4 is equal to 2 pi over 3 plus k pi. K for all solutions, pi is the period. How about this one? Theta over 4 equals 5 pi over 3 plus k pi. Again, pi is the period, k gives us all the solutions. Have we answered the question for all solutions of theta? No. Because what we have is theta over 4, not theta. So what do we need to do? Multiply both sides by 4. By 4, we have the solution for all theta. So multiply this by 4, we get theta. Then we have 8 pi over 3 plus, of course, 4k pi, right? 4k pi. Here, we can, because the period of, see, it's also shown in the graph. It's implied in the graph as well. Because the solutions are 2 pi over 3 and 5 pi over 3, then the difference from this angle to this angle is simply pi, right? And tangent has period pi. So we can, if we want to, keep this and say theta is equal to 20 pi over 3 plus 4k pi. But it's not necessary because here, let's see, if we have 2 pi over 3 plus pi. Yeah, because it's not necessary because this one will cover this one anyway. So well, let me do it this way. So it's not, so for the sake of your notes, it's clear. So we have theta equals 20 pi over 3 plus 4k pi, right? But because the period is pi, and from the diagram we can see that if you have this one, you add pi to it, you get the other one. So this one automatically covers that one. So let me call this equation 1. Equation 1, and this equation 2. And say, note, here this, because you can keep this, but it's redundant. You don't really need this. These angles are already covered by this one. So equation 1 already covers the solutions by equation 2. So the only solution is really the so if we say, so the only solution we have is just theta, not this, sorry, theta is equal to that one. So let's keep that one. 8 pi over 3 plus 4k pi. That's all the solutions. That's all the solutions. So that, let me use my thicker marker here because that's 3. 8 pi over 3. And k is any integer. So we don't need that one. So then for specific solutions within 0 to 2 pi, so let's see if which k values we should have for 0 to 2 pi. So for this interval, we cannot go beyond 2 pi. We can be 0, but we cannot go beyond 2 pi, or this interval. So if k is equal to 0, this term drops out. What about this term? 8 pi over 3 is already outside of this interval. Isn't that interesting? Because 8 pi over 3 is larger than 2 pi, right? It's 2 point something pi, right? I don't have my calculator with me, but 8 over 3 would be, it would be 2 point, maybe 2.7 something. No, actually less than that, 2.6. So 2.6 something. So it's beyond 2 pi. It's 2.6 pi. So this is already, even if k is equal to 0, This piece is outside of this interval for theta. So there is no solution for this within this interval. Okay? Let's write that down. So because for any k value, including the one that I just mentioned, including k equals 0, this quantity, theta 8 pi over 3 plus 4k pi, will be outside of 0 to 2 pi. Thus, there is no solution for theta within 0 to 2 pi. Okay? So, no solution for that. So next example, and I want to, please excuse me while I'll drink a little bit of water here. All right, so the next example then, we have given 4 sine of theta cosine of theta plus 2 sine of theta minus 2 cosine of theta minus 1 equals 0. Given this equation, we want to find all solutions of theta, and B, all solutions of theta within 0 to 2 pi. Okay? All right, so the solution here. So here in this equation we have how many terms? 1, 2, 3, 4, right? 1, 2, 3, and this -1 is the fourth term. Now, so far, what we've done, anytime we had more than one type of trigonometric function, like we have in this case, sine, cosine, we have two trig functions, sine and cosine. We always converted one into the other in order to solve the equation. So sometimes, though, it's possible to keep both trigonometric functions and still solve the equation. But then we have to use other techniques to factor the equation. As long as we can factor the equation, we can find solutions of theta. Now, because we have 4 terms from basic algebra or Math 126 and even Math 124, we discussed the method for factoring equations where we have 4 terms. Do you remember what that method is? It's grouping, right? We can group any 2 terms we might be able to factor the equation. It's a technique we can try, but we can only try it when we have 4 terms, at least among the examples we've done. Right? The largest equation that we've factored without using the long division or synthetic division was when we had 4 terms in it. Here, let's try factoring by grouping. So I'm just going to say, recall that when we have 4 terms in an equation, we may be able to factor the equation using a grouping of terms. So here, let's group these two together because they seem to have this common factor 2 sine theta, right? 2 sine theta is a common factor of this term as well as common factor of this term. Let's see if we can simplify the expression that way. So 2, let me start here. So we have 2, factoring 2 sine theta from the first 2 terms. We have 2 cosine of theta plus 1, right? If you distribute this 2 sine theta into these 2 terms, you're going to get these 2 terms back. How about these 2 terms? Can we factor anything from these? Yes, we can factor out negative. So minus, if you factor the minus 1 out, what do you get? You get 2 cosine theta plus 1 and 0 on the other side. Now, let's step back and look at these terms. Certainly, 2 cosine theta plus 1 and 2 cosine theta plus 1 is common to both of these, right? So let's factor out 2 cosine theta plus 1 from both terms. So we have 2 cosine theta plus 1. From this term, we end up with 2 sine theta, and then from here, we end up with minus 1 equals 0. Look at that. We now have the original expression, that one, fully factored here. And that's all we need to solve for theta. So from here we can solve for theta, and from here we can solve for theta, right? So let's do that. So here, if 2 cosine theta plus 1 equals 0, then cosine of theta is equal to minus 1/2. Now, this is an easy number. Where do we have where cosine is negative? Well, cosine is negative in the second quadrant and the third quadrant, right? So that would be 2 pi, and cosine of pi over 3 would be 1/2, but that would be positive in the first quadrant. So in the second quadrant, it would be 2 pi over 3. So maybe I should draw a little figure here, little diagram, like that. So we know that cosine of pi over 3 in the first quadrant is equal to 1/2, because we're looking for this angle for which cosine is 1/2. For a second, disregard that minus. Pretend that it's not even there. So cosine of what angle is 1/2? Pi over 3, right? We know that from the table of special trigonometric values. But that would be positive, so we need the angle to give us a cosine value that is negative, and that would have to be in the second quadrant and the third quadrant, because in these 2 quadrants, here and here, the cosine or the x-axis is negative. Okay? Only in the second quadrant and the third quadrant, the cosine or the x-axis is negative. That one and that one. These two angles. That one and the larger one. That one is 2 pi over 3. You can easily find it by saying pi minus pi over 3. You get that. And then this one is pi plus pi over 3. And you get 4 pi over 3. And that's that angle, the larger one. Not the smaller one, the larger one. Okay? So, therefore, from here and from this little diagram, we can say that theta then must be equal to either 2 pi over 3 comma the other one, or 4 pi over 3. Then we have another one here, another factor here that we need to find theta from this equation. So if 2 sine theta minus 1 equals 0, then that means if we solve this algebraically, we get sine of theta equals 1/2. Well, sine of which angle is positive 1/2? We already know that, right? Let me, just like this, let me draw a small diagram here. The sine or the positive or the y-axis is positive in 2 quadrants, either the first quadrant or the second quadrant, right? The sign would be negative here because the y-axis would be negative here in these 2 quadrants. So we're dealing with either here or that. So we're going to have solutions for this equation in the first quadrant and the second quadrant. One solution, because this is such an easy number, this 1/2, we know that sine of pi over 6 is positive 1/2. Okay? So that angle is that one. And that's pi over 6. So sine of pi over 6 is 1/2. The other sine or angle value that is going to give us a positive 1/2 value is in the second quadrant, which is this angle. What is that angle? That angle is pi minus pi over 6, right? This piece is 1 pi over 6. Pi over 6. This piece that the terminal angle did not go through is pi over 6. It stops there. So pi minus pi over 6, or 5 pi over 6, is the other angle. So sine of pi over 6 is 1/2. Because the y-axis in that quadrant is positive. Sine of pi over 6 is also 1/2, 5 pi over 6, because the y-axis in this quadrant is also positive. All right, so from here then, from this equation, we know that theta must be equal to either pi over 6 or 5 pi over 6. Okay? So now we know that the period for both sine and cosine is how much? Do you remember? It's 2 pi. So let's recall that the period for both sine and cosine function is 2 pi. We're going to need to remember that when we write all solutions. Okay? So we're going to have these two plus 2k pi and these two plus 2k pi as well. So let's write that down. So we have from here we have let me, maybe I should. So from here, and then from here, we have theta equals 2 pi over 3 plus 2k pi, and theta is equal to 4 pi over 3 plus 2k pi. Okay, on this side, from these two solutions, we can write theta is equal to pi over 6 plus 2k pi, and theta is equal to 5 pi over 6 plus 2k pi. Okay, and we have all these solutions, and k is, of course, any integer. Okay, that's all the solutions for that equation. Now to find, so part B, we're looking for solutions for within the interval 0 to 2 pi, right? So B within the interval 0 to 2 pi. So let me bring back my scratch paper here to get an understanding of what k values we should use. So remember, we're looking for all the solutions within this interval, knowing that we cannot be outside of this interval. Okay, so for k equals 0, this term drops out, and we get 2 pi over 3, 4 pi over 3, those two, and these two, pi over 6 and 5 pi over 6, all those four are within this interval. So for k equals 0, we're okay. How about k equals 1? If you put k equals 1 in any of these, you're going to be equal to 2 pi plus some more. So you're going to be outside of this interval, and so it's not acceptable. So any k value equal to 1 and higher is not acceptable because it'll take you outside of this interval. For solutions within this interval, we only need to set the k equal to 0. That's it. Okay? So, simply set k equals 0, and we have these solutions. You have the equations right there. So we have theta equals, put 0, you end up with the original solutions that we had, right? 2 pi over 3, 4 pi over 3, 5 pi over 6, and pi over 6. That's all. So we have that. I'm going to start from here, and then this, and then this, and that. Or 2 pi over 3, pi over 6, and like that. Makes no difference. But 2 pi over 3, pi over 6, 4 pi over 3, and then, of course, 5 pi over 6. Okay, so these are all the solutions within the interval 0 to 2 pi. All right, so suppose then here we have given this function f of x equals sine of 2x plus 1, and g of x equals 2 sine of 2x plus 1, we want to find the intersection points. Intersection points of function f and g. I mean, this is a really easy question, right? We've done this many, many times in basic algebra. If you're finding the intersection of two functions, basically they're asking you to set up a system. So we set up this equal to that. It's very easy. So find the intersection points of f and g algebraically. Okay, so the solution is so let's set these two functions f and g equal to each other because we're looking for for where they intersect. And that one, 1, and then we have, let's move everything to one side and set it equal to 0. Minus 2 sine 2x minus 1 equals 0. Minus 1 plus 1, 0. And then sine of 2x minus 2 sine 2x. It's going to be minus sine 2x equals 0. Which is really, we can divide both sides by minus 1. And we get sine of 2x equals 0. So there are many solutions possible, right, for this intersection. So there are many points where these two functions intersect each other. Why? Because then sine from this, then based on this equation that we have, then 2x can be equal to 0, can be equal to pi. For all these values, this equation is true. So 0 pi, 2 pi, 3 pi, and then let me put ... all the way to k pi, where k can be any integer. For k again, any integer, right? So have we answered the question, this question here? Not yet. Why? Why do you think not? Well, when they say solve this, what do? We solve for x when these two are set equal to each other. But have we found x yet? No. We found 2x should be equal to that. If in this equation 2x is equal to any of this, we're going to have, yes, this equation will hold. But we need to find what x is going to be. So how do we do that? Divide both sides of this equation by 2. So dividing both sides by 2, we have, so we're going to have on the left, we're going to have x. On the right, we're going to have 0, pi over 2, pi, right? 3 pi over 2, comma, ... k pi over 2, or 1/2 times k pi. So k pi over 2. Okay? So basically, then, so these are all the x values, right? If you plug in x value here with, let's say, pi over 2, right? That's one of the solutions, x equals pi over 2. But what is the intersection point? So we need to calculate the y value. So for one of these, calculating the function value for one of these, or gx, it makes no difference which one of these you do. I'll just do f, but you calculate g of x at any of these values, you get the same value that you would get for f, because that's the point of intersection. At that point, both functions give us the same value. So calculating the function f of x or g of x at any of these x values gives us the intersection, the function value at the point of intersection. Okay, so like I said, I picked, I'm going to pick f of x, which was sine of 2x plus 1 at x equals, let's say, pi over 2. Okay? We do 1, it's true for all of them. So then that would be f at pi over 2. We have sine of 2 times 2 pi over 2. Instead of 2x, we get 2 pi over 2 plus 1. So sine of 2 and 2 cancel out. Sine of pi is 0 plus 1 is 1. Right? So, thus, we move this up a little bit. So the points of intersection are k pi over 2 comma 1. Okay, and k pi over 2, I just took that because if you and k is any integer, right? So if k is 0, you get 0. If k is 1, you get pi over 2. If k is 2, you get pi. If k is 3, you get 3 pi over 2. So this one takes us through all the possible values for x. So that's why x values can be anything. With I can add, if you want. I've said it above, but we can also say that k, any integer. We can further clarify our answer there. So that's all the x values, and whichever one you pick, the function value is always 1. All right, so let's now switch to other types of examples. But these examples, again, we're going to solve for theta using those techniques that we've learned in the past. We're not learning anything new here. We're just applying using the tools we've been introduced to. That's all. And this is just using other tools we've learned about. So use, I need to, let's do another. I missed one example. Fortunately, I just caught it. So let me do that example, actually. I almost missed it. Sorry about that. So I'm going to go back to it. This is similar to what we just did. the one we just did, that given these two, find the intersection points. We're going to do another example just like this. So once again, given this function, 3 cosine of x plus 1, and g of x equals cosine of x minus 1, find the intersection points of f and g algebraically. Okay, just like before, that means we need to first set those two equations equal to each other and solve for x. So we have 3 cosine of x plus 1 equals cosine of x minus 1. Let's move everything to one side. Plus 1 minus cosine of x plus 1 minus cosine of x equals that. And then so we have 3 cosine of x minus cosine of x, that's 2 cosine of x. 1 plus 1 is 2 equals 0. And then 2 cosine of x equals to minus 2, and then therefore cosine of x equals minus 1, right? So at which point cosine of an angle is equal to negative 1? We know from the table of special trigonometric values that from that x should be equal to pi. Okay, so let's also recall that cosine of x has period. Do you know what period it has, the cosine function? 2 pi, right? We know that. 2 pi. And so thus we have so then, but we're looking for the point of intersection. So we found, so this would be pi plus 2k pi. We already know what x values are going to look like. They're going to be pi plus 2k pi. But what about the y value? So we can take any of these functions. It makes no difference which one. I'm going to take the first. Last time, in the last example, I took f of x, and this time I'm going to use g of x to find the value of the function at the point of intersection between these two functions. So we have using g of x this time equals cosine of x minus 1 at x equals pi. Let's just take pi. Okay, we can take 2 pi, 3 pi, whatever, but let's just pick the easiest one. Then that, what are we going to get from this? We're going to be g at pi is equal to cosine of pi minus 1. Cosine of pi is minus 1, minus another one, minus 1, we get minus 2. And that's true for all possible x values. So thus, all points of intersection of f and g of f and g, here, g, are, so we say pi plus the period 2k pi, gives us all the possible intersections, comma -2. Like that. And k, of course, is any integer. Any integer, okay? All right. So next, we're going to switch gear to, like I was saying, we're going to use some of the other formulas we've learned in the past in solving trigonometric equations. That's all. So use addition or subtraction formulas. Remember those? Okay, so we have, here's the equation we have. We have cosine of theta times cosine of 2 theta plus sine of theta times sine of 2 theta equals 1/2. Okay. Actually, this is not part of the solution, sorry. This is what this was given to us. So we're going to apply the solution to this. So I'll just put an arrow to clarify. So this is where the solution will begin. And I'll put a dashed line here. All right. So recall, this is obviously the addition formula. So recall that what we used to have was that the formula cosine of x minus y equals cosine of x times cosine of y. This is minus, and then this is plus sine of x times sine of y. That was the original formula we introduced. Okay, the original addition formula. So in this case, now compare this with what we have here, right? Cosine times cosine plus sine times sine, right? So that in this case, the theta here is x and 2 theta is y. So let me write that down. So we have x is equal to theta in our case. And this is the general case. This is our example. And y is equal to theta in our case, right? Therefore, so then we can rewrite that equation that we were given in a new form. We can write it as cosine of theta minus 2 theta. And if you expand this, you're going to get that according to this formula. We have the right-hand side, and now we're going to convert it to this form. Is equal to the right-hand side, which is 1/2. Okay? So therefore, from that, we can tell that cosine of negative theta is equal to 1/2, right? Right, like that. So now cosine of what angle gives us positive? Well, actually cosine of, let's recall this. So recall that cosine is an even function. Recall that cosine of minus theta is equal to cosine of theta because cosine of x is an even function. Even function, okay? So we can rewrite this as cosine of theta equals 1/2. Well, where do we have cosine of theta equaling 1/2? Let's draw a quick diagram to visualize that. Cosine refers to the x-axis, right? In which quadrants is the cosine of theta positive? Never mind what value, but where is it positive? In here, in the first quadrant, and also in the fourth quadrant, right? That's where the x-axis is positive, which is associated with the cosine. So now we think about what angle value has a cosine equaling 1/2, and that would be pi over 3, right? So we can say pi over 3, that angle, pi over 3, and this angle, that's 2 pi minus pi over 3, right? This angle, this larger one, is 2 pi minus pi over 3. So it'll be 2 pi minus pi over 3 equals 5 pi over 3. That's the bigger angle. So those are the angles for which cosine is positive 1/2. Okay? But this one, remember that this one is asking us for the solutions in the interval 0 to 2 pi. So we don't have to find all solutions with the k involved, k being any integer. So all we say is that the solutions are pi over 3 and 5 pi over 3. So thus, within this interval 0 to 2 pi, all solutions of theta are as follows. Theta is equal to pi over 3 and 5 pi over 3. The emphasis is this, that we're talking about these solutions of that equation within this interval. Okay, and there's just two of them. All right, so we have in this example, we want to use a double or half angle formula in the interval 0, 2 pi. Okay. for, and here's the equation, tangent of theta over 2 minus sine of theta equals 0. Okay, so here we have a solution. And then, so this is one of those cases where it's better to use the half angle formula that we have, right? We have a formula for the tangent half angle. So let's recall that. Recall that tangent of half angle is equal to 1 minus cosine of theta divided by sine of theta. Tangent half angle, I think, has 3 different formulas. So you can pick whichever one you think is more useful. I think I picked this one. There is one that says, I think, I'm not sure, sine of theta over 1 plus cosine theta. That's another one. So you can use that if you like. So I'm using this one. So let's replace tangent of half angle, theta over 2, with this equivalent in here. Okay, so we have 1 minus cosine of theta divided by sine of theta minus sine of theta equals 0. Okay, then of course we can, since we're going to solve this for theta, we're going to take the common denominator. And so we have sine of theta, and then here we have 1 minus cosine of theta minus sine squared theta, right, equals 0. Let's see if I did this correctly. Let's see, sine of theta 1 minus let's see, 1 minus, let's see, yes, so that's correct. So let's multiply both sides by sine theta. This is just the techniques we've used in basic algebra. Multiply both sides by whatever is in the denominator, and we get 1 minus cosine of theta minus sine squared theta equals 0. Or we can then say so let's see. So let's say 1 minus then cosine of theta is equal to sine squared theta. Okay. So now we have an equation here which is more simplified than this, yet we still have sine squared and then cosine, the linear cosine theta and then sine squared theta. Let's try to convert this to just one trigonometric function. And this one allows us to do that. So let's recall that sine squared theta, that's what we have on the right side, plus cosine squared theta equals 1. Therefore, we can solve for sine squared theta in terms of the cosine squared theta. So 1 minus cosine squared theta. So in here, in this equation, in this last equation that we simplified, let's, on the right side, let's replace for sine squared theta with 1 minus cosine squared theta. Okay? So, let me use that arrow to clarify. So from here, we have 1 minus cosine of theta equals, let's replace that with this, 1 minus cosine squared theta. Okay, so now let's move everything to one side and set it equal to 0 and solve it that way. So cosine squared theta and minus cosine theta is already on that side. I'm trying to save space by doing it all, simplifying at the same time. I don't recommend that you always do that, but I'm just trying to save space. But it causes error when you try to combine several steps in one step. So it's better to do it step by step. So then also 1 and minus 1 add up to 0, so we end up with 0, cosine squared theta minus. So let's factor cosine theta out. Obviously we can do that here. Cosine theta factored out, we have cosine of theta minus 1 equals to 0. Then from here, if cosine of theta is equal to 0, then theta can be either equal to pi over 2 or 3 pi over 2. And remember, we're looking for the solutions within 0 to 2 pi, right? Within 0 to 2 pi. So pi over 2, within that interval, 0 to 2 pi, both of these solutions are within that. From here, if cosine of theta minus 1 equals to 0, then cosine of theta equals 1. And so that would be within the 0 to 2 pi interval, then we have theta equals 0. Okay? So within, then theta is equal to 0, pi over 2, and 3 pi over 2 within 0 to 2 pi. So I'll just leave it at that. Those are the three solutions within the interval 0 to 2 pi. Okay, so another example. Here, so we want to solve 2 sine squared theta equals 2 plus cosine 2 theta for values of theta on this interval again, 0 to 2 pi. Okay. Okay, so let's see. So we have a double angle here, and we have a sine squared here. So we definitely want to convert one to the other in order to be able to solve for theta. So let's recall the double angle formula for cosine 2 theta. So recall that, and we have, I think, cosine double angle has two or three different formulas. So cosine 2 theta is equal to, yes, so there are several kinds of several of that formula for cosine double angle. So I'm using this one. So 1 minus 2 sine squared theta. So we're going to replace in here with this equivalent of it. So therefore we have 2 sine squared theta equals 2 plus all of that, 1 minus 2 sine squared theta. Okay. of course, after we do simplification and all of that, so we get 2. This 2 plus 1 is 3. Minus 2, bring it to this side, we get 4 sine squared theta equals 3. This is just after algebraic manipulation, that's all. Then, from here, then, we have sine squared theta is equal to 3 over 4. Therefore, sine of theta is equal to plus or minus square root of 3 over 2 by the square root property, right? Plus or minus. So this is plus and minus. And that's within 0 to 2 pi. So within 0 to 2 pi, then, we're looking for all angles such that for which the sine would be plus or minus square root of 3 over 2. So that's basically all quadrants, right? In all quadrants in the unit circle, we either have sine of theta equaling the positive square root of 3 over 2 or negative 1. So this covers all quadrants. So let me write that. That result this result has a solution in all quadrants of the unit circle. Okay? Because it's plus or minus. And so, and what are those? In a period of sine is 2 pi. We already know that. And so what are, and since I mentioned this, so let's see what are those solutions. Let's see, we can either, so let's see, so if we draw a little circle here, and we're looking for solutions within 0 to 2 pi, and if I draw a little circle here, let's suppose this is the unit circle with radius 1, then the sine of pi over 3 is a positive square root of 3 over 2. So we can have pi over 3, and that's in first quadrant. What's the solution in the second quadrant then? Since we have a solution in every quadrant, and then that would be 2 pi over 3. That would be that angle, 2 pi over 3. What's the solution in the third quadrant? That would be 4 pi over 3. So this would be here, pi plus pi over 3, we get 4 pi over 3. And then what's the solution in the fourth quadrant then? So that would be, and so that would be that. And then, of course, we have that one as well, this big angle, which would be 2 pi minus pi over 3. 2 pi minus pi over 3, so that would be 5 pi over 3. So that would be that angle here, 5 pi over 3. Okay? So there are many, many solutions of this. If we use the k for all solutions, we end up with many solutions. But within 0 to 2 pi, which is what they're asking, the solutions are in front of us. So these are the, thus, within 0 to 2 pi, we have theta equaling pi over 3, 2 pi over 3, 4 pi over 3, and then of course 5 pi over 3. Okay, that is within 0 to 2 pi. All right, so then another example. So we want to solve the equation by using a sum to product formula. And so this is the equation that we have. We have cosine of 5 theta minus cosine of 7 theta equals 0. Okay? So we remember that one of the sum to product formulas that applies to this is this one. So recall that we have cosine of x minus cosine of y equals minus 2 sine of x plus y over 2 times sine of x minus y over 2. Okay? We have that formula. Then, so let's apply that here. For our case, x is 5 theta and y is 7 theta. So here x is 5 theta and y is 7 theta in the case of our own equation here. So we're going to apply that. And so therefore, so after all that, we have cosine of 5 theta minus cosine of 7 theta equals minus 2 sine of 5 theta plus 7 theta. All right, I'm just substituting for that. Divided by 2 times sine of 5 theta minus 7 theta divided by 2. Okay, so then what do we get? We get minus 2 sine of 12 theta over 2. That's 6 theta, right? 6 theta sine of 5 theta minus 7 theta. That would be minus theta. So we know that sine function is an odd function. So sine minus theta is equal to minus sine theta. So recall that sine minus theta is equal to, sorry, I should put that here, minus sine theta, because sine theta is an odd function. Okay, so that means that minus can come out and multiplies itself by this minus and makes it positive. So we have then 2 positive. From minus 2 we went to positive 2 sine of 6 theta sine of theta. Okay, that was the reason why we recall that. Okay, and of course this will be so this is all the left hand side, right? we simplified this left-hand side using this sum to product formula to this. But that was equal to 0. So we need to set this equal to 0. Therefore, we have 2 sine of 6 theta sine of theta equals 0. Okay? So this is already in factored form. And so we can say that this equation is true when 6 theta equals 0, or theta is equal to 0. But when will that happen? When this argument of either function is either equal to 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, all of that. So what does that mean? That means that wherever we have the equation, wherever we have k pi or multiples of pi in either argument, this equation is valid. So for this piece, well, let me, from here and from here, this means that 6 theta is equal to, whenever 6 theta is equal to k theta, k pi, or whenever 0 or theta is equal to k pi. So any multiples of pi where k is in any integer, this equation is valid. Okay? For either argument. So from here then, what do we get for theta? We get 1 over 6 k pi. How about here? We already have k pi. Okay? So these solutions are already covered, and let me label this as equation 1. That one. These solutions are already covered by equation 1. Let me move this up a little bit. Equation 1. That one. Okay? Because of that, then this is really redundant. We don't need that. Because k is any integer. Remember, k is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever. Either positive or negative. But when k, for example, when k here is 6, right? 6 would make this pi, theta equals pi, which would be equivalent to k being 1 for this one. K equals theta equals pi. So this covers this and more solutions. So all we need is this one. Okay? And they don't specify, the problem does not specify, find the solutions between 0 and 2 pi. So we're giving all the solutions. Thus, all solutions of theta are covered by 1 over 6 times k pi. Okay? So you can keep that. You can write this also in addition to this, but it's redundant. This is going to hit that and more. Okay? All right. Okay, so in this next example, we want to solve like that. We want to solve that for values of theta, of course. And so here, again, we have a one of those formulas, formulas that we can convert to a product, right? Sum to product formulas. We can apply that. For this one, let's recall that this is the difference between two sine functions. So this is the one we want to use, sine of x minus sine of y equals 2 cosine x plus y divided by 2 sine of x minus y divided by 2. That's the one we want to use. Okay? So in our case, of course, the x is 5 theta and y is 3 theta. Okay? Therefore, we have, instead of that, I'm going to convert the left side to that. So we're going to have 2 cosine of x plus y, 5 theta plus 3 theta. Right? We're writing the equivalent of this in product form because the left sides match. Okay? That's what we're doing. So that and sine of 5 theta minus 3 theta equal the right hand side, which is cosine of 4 theta. Okay, so let's simplify. We have 2 cosine of this is 8 theta over 2, which would be 4 theta. Sine of 2 theta over 2, which is theta, equaling the right side, which is cosine of 4 theta. Okay? And well, let me put the arrow here because this is where the equation is, not here. Okay, so let's move. We have a cosine 4 theta here and a cosine 4 theta here. Looks like we can factor things out if I move this to the left. So we have 2 cosine of 4 theta sine of theta minus cosine of 4 theta equals 0. Now let's factor out cosine 4 theta times 2 times sine of theta minus 1 equals 0. Well, now everything is in, and also remember that here it doesn't say find the solutions within 0 to 2 pi. So we need to find all solutions which involves k, any integer, right? So just keep that in mind. So this equation is in factored form, so let's solve it. So if cosine of 4 theta is equal to 0, then for what values of this argument cosine is 0? So cosine is 0 when we have pi over 2 and 3 pi over 2, right? So 4 theta, if 4 theta is equal to pi over 2 or 3 pi over 2, the cosine of that would be equal to 0. And how about here? And we'll involve k later, but let's see what we have here, what kind of solutions we have here. So if 2 sine of theta minus 1 is equal to 0, then sine of theta equals 1/2, then theta must be either pi over 6 or 5 pi over 6. Right? Those are the two angle values for which the sine is positive 1/2. Okay? Within from 0 to 2 pi. But now we know that, so recall that both the sine and the cosine function have period. Do you remember what period they have? 2 pi, right? Tangent and cotangent have period pi. Sine and cosine have period 2 pi. Okay? And we know that because cosecant is the reciprocal of sine, so that cosecant function also has a 2 pi period. We know that secant function is a reciprocal of the cosine function, so secant function also has a period 2 pi. Okay, it makes it easy to remember which functions have what period. Okay, so now we have then, so we have, let's see, so thus, thus we have from this side and from this side. Okay, so we have 4. We have 4. Let me move this up a little bit, maybe. 4 theta equals pi over 2 plus 2k pi, and also 4 theta equals 3 pi over 2 plus 2k pi. Okay, that's all the solutions from this one. And so let's see. So if we have okay, so for solving for theta then we have, okay, so it looks like again what's going to happen is this one, yes, this one is going to cover this. Okay, so even though this is correct, but this is, once we solve for theta, this is going through this one as well. So we really need, so let me actually, so equation 1, let me call this equation 1. It's not that it's incorrect if you keep this, it's just that it's redundant, because this is covering that anyway. So all we need from this bunch of solutions, all we need is the first one. We don't really need that. That's all. So equation 1 and equation 2. So all we need, equation 1 covers the solutions by equation 2. Okay, this one doesn't cover those solutions. The equation 1 covers more solutions than this one. This one including its own. So then let's, how do we solve for theta? Because we need to solve for theta. We multiply both sides by 1 over 4. So when we do that, let's do it for just that one. We're going to, because that's going to cover this. So theta is equal to pi over 8 plus 1/2. Let's see. So 1/2 over, do we have 4 theta? Pi over 2. So we have pi over, and let's see, 2k pi. So we have 1 over 2 k pi. Okay, so that's just multiplying. I'm just double checking this. 1/4 pi over 8, and that one, which is 1 over 4. Yeah, that would be correct. So this is that. And from this side, then, we're going to have theta equal, like that. So theta equals pi over 6 plus 2k pi. That's another set of solutions. And of course, the other one, which is theta equals 5 pi over 6 plus 2k pi. Like that. Okay, so I think that should do it, yes. So pi over 8 over half k pi. All right, so these three solutions together form, and k being an integer, give us all the solutions of that original equation. So any integer. Okay, I'm just double checking here for, so plus 2k pi, and then 1/4. That should be correct. All right, so I thank you for watching this video until the end, if you need it. As I said before, I'm solving more examples during these videos because more people find it helpful if they see more examples. But you don't, if after a few examples you feel that you completely understand the topic, then you obviously don't have to go through this long videos like this one. This one I felt that I needed to solve a lot of examples in order for people to understand the material, and I hope it accomplished the objective for which this video lesson was intended. If you have any questions, I trust that you will let me know. So for now, have a nice day, and I'll see you again next time.